On December 27, 1942, the first prototype of what would become the Kawanishi N1K-J Shiden lifted off from Itami Airport, representing the culmination of Japan's most ambitious fighter development program. The aircraft embodied a revolutionary design philosophy that placed unprecedented trust in automated systems to manage the complex aerodynamics of high-performance flight. Where previous fighters relied on pilot skill to manage basic flight characteristics, the N1K-J incorporated automatic combat flap systems, sophisticated hydraulic control architectures, and integrated subsystems designed to enhance pilot effectiveness through mechanical intelligence. The engineering team at Kawanishi, led by a cadre of designers who had previously worked on seaplane fighters, approached the N1K-J project with fundamental assumptions about how automation could solve the operational challenges facing Japanese pilots in 1942. The Imperial Japanese Navy had specified requirements for an interceptor capable of matching the performance of American carrier-based fighters, while being operable by pilots with increasingly limited training time. The solution, as conceived by chief designer Shizuo Kikuhara and his team, centered on creating an aircraft that would automatically compensate for pilot limitations through sophisticated mechanical systems. The automatic combat flap system represented the cornerstone of this design philosophy. Unlike conventional aircraft, where flap deployment required conscious pilot input based on airspeed and tactical requirements, the N1K-J incorporated a complex hydraulic mechanism that automatically adjusted wing configuration based on manifold pressure and airspeed inputs. This system was intended to optimize wing efficiency across the entire flight envelope without requiring pilot intervention, theoretically, allowing pilots to focus on tactical decisions rather than flight management. The engineering logic was elegantly simple. If the aircraft could manage its own aerodynamic configuration, pilot workload would decrease, while overall performance would increase. The hydraulic architecture supporting this automation represented an unprecedented level of complexity for Japanese fighter aircraft design. The system incorporated dual hydraulic circuits operating at 1,000 pounds per square inch with automatic pressure regulation, thermal compensation, and integrated failure detection. Hydraulic power operated not only the automatic flaps, but also the landing gear, gun charging mechanisms, and primary flight controls. The engineering team designed this architecture based on the assumption that hydraulic reliability could be ensured through redundancy and precision manufacturing, creating a system where multiple failures would be required to compromise aircraft safety. However, the design assumptions underlying this sophisticated automation were calibrated to testing conditions that inadequately represented the thermal and mechanical stresses of extended combat operations. Laboratory testing and initial flight trials validated system performance under controlled conditions with predictable load factors, regulated temperatures, and routine maintenance intervals. The hydraulic components functioned flawlessly when operated within design parameters, leading the engineering team to conclude that the system's complexity was justified by its reliability under normal operational conditions. The critical assumption embedded within this design philosophy was that combat operations could be treated as an extension of test conditions rather than a fundamentally different operational environment. Engineers calculated hydraulic system reliability based on component specifications derived from ground testing and short-duration flight trials. These calculations assumed that thermal cycling, vibration loading, and fluid contamination would remain within predictable bounds even during extended high-G maneuvering sequences. The precision tolerances required for proper hydraulic valve operation were established based on laboratory conditions where temperature variation, fluid purity, and mechanical vibration could be controlled. This assumption extended to the aircraft's instrumentation and pilot interface design. The cockpit incorporated sophisticated pressure gauges, flow indicators, and warning systems designed to inform pilots about hydraulic system status. However, these instruments were calibrated to detect failures that matched the engineering team's understanding of how hydraulic systems could malfunction. Pressure sensors monitored line pressure but provided no information about fluid state, internal leakage rates, or thermal effects on component clearances. Flow meters detected gross leakage but were insensitive to the micro-scale internal bypassing that would prove critical under thermal stress conditions. The training doctrine developed for N1K-J pilots reflected these engineering assumptions about system reliability and failure modes. Pilots learned to trust the automatic systems under normal conditions and to recognize specific warning indications that would trigger manual override procedures. Emergency training focused on obvious failure scenarios, complete hydraulic pressure loss, stuck flaps, or total system shutdown rather than the subtle performance degradation that would characterize actual combat failures. This training approach assumed that system failures would be binary and detectable rather than progressive and ambiguous. Manufacturing protocols for the N1K-J's hydraulic components emphasized precision assembly and quality control procedures designed to ensure that components met design specifications. Tolerance requirements were established based on engineering calculations that assumed uniform operating conditions and predictable wear patterns. Quality control testing validated component performance under laboratory conditions, confirming that manufactured parts met design requirements for pressure containment, response timing, and operational reliability. However, these manufacturing standards made no provision for the accelerated wear patterns and thermal stress effects that would emerge under sustained combat loading. The organizational structure supporting N1K-J development created additional layers of assumption about system reliability and operational effectiveness. Engineering teams focused on meeting performance specifications established by the Imperial Japanese Navy, while manufacturing teams concentrated on achieving production targets under wartime resource constraints. The feedback mechanisms between operational units and design teams were limited, creating an information gap where field experience could not effectively inform design modifications or training updates. This organizational separation reinforced the assumption that laboratory-validated designs would perform reliably under operational conditions without requiring significant modification based on field experience. The fundamental design assumption underlying the entire N1K-J program was that sophisticated automation could eliminate operational unpredictability while enhancing pilot effectiveness. Engineers believed that by automating flight management tasks, they could create an aircraft that would perform consistently regardless of pilot skill level or combat conditions. This assumption was reinforced by early test results that demonstrated superior performance compared to conventional fighters when operated under controlled conditions. The success of these initial tests validated the engineering team's confidence in their design approach and supported the decision to proceed with full-scale production. However, this design philosophy created a hidden vulnerability that would only manifest under conditions that exceeded the assumptions built into the system architecture. The automatic systems that provided enhanced performance under normal conditions became sources of unpredictable behavior when operating parameters exceeded design envelopes. The sophisticated instrumentation that accurately reported system status under laboratory conditions provided misleading information when thermal effects and mechanical wear altered component behavior. The training protocols that prepared pilots to manage obvious failures left them unprepared to recognize and respond to progressive system degradation. The transition from prototype testing to operational deployment revealed the first indications that the design assumptions might be incomplete. Early service trials conducted by experienced test pilots under carefully controlled conditions continued to validate the aircraft's performance capabilities. However, reports from operational units began to include references to handling characteristics that seemed to vary unpredictably during extended flight operations. These variations remained within acceptable limits and were often attributed to normal operational factors such as fuel consumption, ammunition expenditure, or pilot fatigue. The engineering team interpreted these reports as confirmation that the aircraft was performing as designed under the variable conditions of military operations. The design assumptions embedded within the N1K-J represented a convergence of engineering optimism, operational necessity, and institutional confidence in technological solutions to tactical problems. The aircraft's sophisticated automation was conceived as a force multiplier that would allow Japanese pilots to compete effectively against numerically superior Allied forces. The complexity of the hydraulic systems was justified by the performance advantages they provided under optimal conditions. The precision manufacturing requirements were accepted as necessary investments in operational effectiveness. These assumptions formed a coherent technical framework that successfully addressed the immediate requirement for improved fighter performance while creating the conditions for systematic failure under stress conditions that exceeded design parameters. The transformation of the N1K-J from engineering concept to operational weapon system created a complex web of latent conditions that would prove critical to understanding subsequent failures. These conditions emerged from the intersection of training protocols, maintenance procedures, and organizational pressures that shaped how pilots and ground crews interacted with the aircraft's sophisticated systems. While the engineering team had successfully created an aircraft with exceptional performance capabilities, the human factors infrastructure supporting its operation was built upon the same assumptions about system reliability and predictable failure modes that characterized the technical design. Pilot training for the N1K-J was developed by a cadre of instructors who had been briefed on the aircraft's capabilities by the engineering team, but who lacked extensive experience with the complex hydraulic systems under operational stress conditions. The training curriculum emphasized the aircraft's automated capabilities as force multipliers that would enhance pilot effectiveness while reducing workload. Pilots learned to trust the automatic combat flap system to optimize wing configuration during maneuvering flight, freeing them to concentrate on tactical positioning and weapons employment. This training approach reinforced the engineering assumption that automation would consistently improve performance without creating new failure modes. The emergency procedures developed for N1K-J operations reflected this confidence in system reliability through their focus on complete system failures rather than progressive degradation scenarios. Pilots practiced responses to total hydraulic pressure loss, stuck landing gear, and frozen control surfaces failures that would be immediately obvious and would trigger clear procedural responses. However, the training program included no provisions for recognizing or responding to subtle performance changes that might indicate developing system problems. The assumption underlying this training approach was that hydraulic failures would be binary events that could be detected through existing instrumentation and addressed through established procedures. Squadron maintenance protocols for the N1K-J were designed around component replacement schedules and routine inspection procedures that assumed predictable wear patterns and failure modes. Maintenance personnel were trained to monitor hydraulic fluid levels, pressure readings, and visual indicators of system status, but they lacked diagnostic procedures for detecting the microscale component degradation that would prove critical under thermal stress conditions. The maintenance approach focused on ensuring that individual components met specifications rather than evaluating system-level performance under varying operational conditions. This maintenance philosophy assumed that properly functioning individual components would guarantee proper system operation regardless of external stresses. The communication structure between engineering teams and operational units created an additional latent condition that would influence failure recognition and response. Formal reporting procedures focused on major malfunctions and performance deficiencies that could be clearly documented and analyzed. However, the reporting system was not designed to capture subtle performance variations or pilot impressions of changing handling characteristics that might indicate developing problems. Pilots who noticed minor variations in control response or system behavior often attributed these changes to normal operational factors rather than potential system degradation, particularly given their training emphasis on trusting the aircraft's automated systems. Organizational pressures within the Imperial Japanese Navy created additional human factors conditions that influenced how pilots and maintenance personnel approached N1K-J operations. The urgent operational requirements facing Japanese forces in late 1943 and early 1944 created pressure to maintain high aircraft availability rates and maximize combat effectiveness. This pressure encouraged tolerance of minor performance variations that might otherwise have triggered more detailed investigation. Pilots were expected to accomplish their missions despite equipment limitations, and maintenance personnel were focused on keeping aircraft operational rather than investigating subtle system anomalies that did not obviously compromise flight safety. The institutional culture surrounding advanced technology within the Imperial Japanese Navy reinforced confidence in the N1K-J's sophisticated systems while discouraging critical evaluation of potential weaknesses. The aircraft represented a significant technological achievement that demonstrated Japanese engineering capabilities, creating organizational momentum toward accepting its performance at face value rather than questioning potential vulnerabilities. This cultural context influenced how both pilots and maintenance personnel interpreted ambiguous system behavior, encouraging them to attribute unusual characteristics to the aircraft's advanced design rather than potential problems. Training scenarios for N1K-J pilots were necessarily conducted under controlled conditions that could not fully replicate the thermal and mechanical stresses of extended combat operations. Flight training missions typically involved relatively short flights with planned maneuver sequences that allowed hydraulic systems to operate within normal temperature ranges and pressure cycles. Combat training exercises, while more demanding than routine flights, still occurred within structured timeframes that limited exposure to the sustained high-stress conditions that would characterize actual combat operations. This training environment inadvertently validated the engineering assumption that laboratory performance would translate directly to operational effectiveness. The diagnostic capabilities available to maintenance personnel reflected the engineering team's understanding of how hydraulic systems could malfunction, but these capabilities were inadequate for detecting the progressive failures that would occur under thermal stress conditions. Pressure gauges provided accurate readings of hydraulic line pressure, but could not indicate internal leakage rates or thermal effects on component clearances. Flow meters detected gross fluid movement, but were insensitive to the microscale bypassing that would characterize thermal degradation. Temperature monitoring was limited to engine and oil systems, with no provision for tracking hydraulic component temperatures that would prove critical to understanding system behavior under stress. The procedural framework for responding to hydraulic anomalies was based on decision trees that assumed clear diagnostic indicators and binary failure modes. Pilots were trained to recognize specific pressure readings, warning light patterns, and control response characteristics that would trigger established emergency procedures. However, these procedures did not account for scenarios where instrumentation provided contradictory information or where system behavior fell into ambiguous ranges that did not clearly indicate either normal operation or complete failure. The assumption underlying these procedures was that hydraulic problems would manifest as obvious malfunctions that could be addressed through predetermined responses. Quality control procedures for N1K-J production incorporated inspection protocols designed to ensure that manufactured components met design specifications and assembly standards. However, these procedures focused on verifying compliance with engineering drawings and material specifications rather than evaluating how components might behave under operational stress conditions. Acceptance testing validated component performance under laboratory conditions, but did not assess thermal stability, vibration tolerance, or long-term reliability under sustained high-stress operation. This quality control approach assumed that components meeting design specifications would perform reliably regardless of operational conditions. The feedback mechanisms connecting operational experience with design modifications were constrained by wartime production pressures and organizational structures that prioritized immediate aircraft availability over long-term reliability improvements. Field reports of unusual behavior or performance variations were processed through administrative channels that filtered out information considered non-critical to immediate operational requirements. Engineering teams received sanitized summaries of operational experience that emphasized major failures while excluding the subtle performance variations that might have indicated developing systematic problems. This information processing structure reinforced the assumption that the basic design was sound and that operational problems reflected external factors rather than inherent system vulnerabilities. Pilot selection and training standards for the N1K-J program reflected resource constraints and operational urgencies that influenced how crews prepared to operate the aircraft's complex systems. Advanced pilots with extensive experience on conventional fighters were often assigned to other critical roles, leaving N1K-J training to pilots with less experience managing complex aircraft systems. While these pilots were capable of learning the prescribed procedures and operating techniques, they lacked the intuitive understanding of aircraft systems that might have enabled them to recognize subtle indications of developing problems. This pilot selection pattern inadvertently created conditions where crews would be dependent on instrumentation and procedures, rather than experiential judgment to assess system status. The technical documentation supporting N1K-J operations was comprehensive in its coverage of normal procedures and obvious emergency scenarios, but provided limited guidance for interpreting ambiguous system behavior or responding to performance variations that fell outside established parameters. Flight manuals emphasized following prescribed procedures and trusting instrumentation readings rather than developing situational awareness based on integrated assessment of multiple system indicators. This documentation approach assumed that comprehensive procedures could account for all operationally relevant scenarios and that pilot judgment should supplement rather than override systematic analysis of instrument indications. The latent conditions surrounding N1K-J operations created an environment where sophisticated engineering solutions were supported by human factors infrastructure that assumed predictable system behavior and binary failure modes. Training protocols, maintenance procedures, organizational pressures, and institutional culture all reinforced confidence in the aircraft's automated systems while providing inadequate preparation for recognizing and responding to the progressive failures that would characterize actual combat operations. These conditions did not constitute design flaws or operational deficiencies, but rather reflected the systematic application of engineering assumptions to all aspects of aircraft operation and support. The operational reality that would expose the N1K-J's hidden vulnerabilities began to manifest during the intensified air combat operations of early 1944, when Japanese interceptor units faced increasing pressure from sustained Allied bombing campaigns. The specific conditions that triggered systematic failures emerged not from single catastrophic events, but from the cumulative effects of extended high-performance flight operations that exceeded the thermal and mechanical assumptions built into the aircraft's design. The divergence between engineered expectations and physical reality began subtly, with performance variations that remained within acceptable limits, while indicating fundamental changes in system behavior. The critical sequence typically began during extended combat air patrol missions where N1K-J aircraft operated at high power settings for periods exceeding normal training flight durations. These missions required sustained operation at combat power levels while maintaining readiness for immediate high-G maneuvering, creating thermal conditions within the aircraft's hydraulic systems that had not been fully characterized during development testing. The automatic combat flap system, which had performed flawlessly during short-duration test flights, began to exhibit response timing variations that pilots initially attributed to normal operational factors such as altitude effects or fuel load changes. Hydraulic pressure sensors throughout these extended operations continued to indicate normal system pressure, providing pilots with instrument readings that confirmed their training expectations about system reliability. The pressure gauges accurately reported the 1,000 psi operating pressure maintained by the hydraulic pumps, and flow indicators showed normal circulation rates throughout the system. However, these instruments measured gross system parameters rather than the thermal effects that were beginning to alter component behavior at the microscale level. As hydraulic fluid temperatures rose above laboratory test conditions, thermal expansion of precision-manufactured valve components began to create clearance changes that allowed increased internal leakage without affecting overall system pressure. The automatic flap system's response to pilot commands during high-G maneuvering began to exhibit subtle delays that remained within the aircraft's specified performance envelope, while indicating significant changes in hydraulic actuator behavior. Pilots noticed that flap deployment during rapid maneuvering sequences occasionally lagged behind airspeed changes, but these delays were typically measured in fractions of seconds and could be attributed to normal system response times under G-loading. The flight manual specified acceptable response ranges that encompassed these variations, and pilot training had emphasized trusting the automated systems rather than attempting to anticipate their responses through manual input. Temperature monitoring systems aboard the N1K-J focused on engine parameters, oil pressures, and cooling system effectiveness, but provided no direct measurement of hydraulic component temperatures that were critical to understanding system behavior under thermal stress. The aircraft's instrumentation package had been designed based on engineering assumptions about which parameters would be most important for flight safety and system monitoring. Hydraulic system temperature had been considered a secondary concern because laboratory testing had validated component performance across the expected temperature ranges for normal flight operations. The progressive nature of thermal degradation in the hydraulic system created conditions where instrument readings remained normal, while actual control authority gradually diminished. Internal leakage within hydraulic actuators increased as component clearances changed under thermal expansion, reducing the effective force available for control surface movement without triggering pressure warnings or flow anomalies. Pilots began to notice that control inputs required slightly more force or produced slightly less response than expected, but these changes occurred gradually enough to be interpreted as normal variation rather than systematic degradation. Flight operations during this period were complicated by the tactical requirements of interceptor missions, which demanded rapid transitions between cruise flight and combat maneuvering that created thermal cycling effects not anticipated during system design. The hydraulic components had been designed for steady-state operation at predicted temperatures, with thermal expansion coefficients calculated for gradual temperature changes rather than the rapid heating and cooling cycles that characterize combat operations. These thermal cycles created metal fatigue effects and clearance variations that progressively degraded component performance while remaining undetectable through existing monitoring systems. Pilots operating N1K-J aircraft during extended missions began to develop compensatory techniques for managing the subtle control response variations they were experiencing. These adaptations represented skilled pilot responses to aircraft behavior that seemed to fall within normal operational parameters, while actually indicating progressive system failure. The pilot's ability to compensate for degraded control authority inadvertently masked the symptoms that might have triggered recognition of developing hydraulic problems, creating a feedback loop where pilot skill concealed system degradation. Maintenance inspections conducted after these extended missions typically focused on routine checks of fluid levels, pressure readings, and visual inspection of external components. The maintenance protocols had been developed based on engineering assumptions about how hydraulic systems would fail, emphasizing detection of external leaks, pressure losses, and obvious component damage. However, the progressive internal degradation occurring within valve assemblies and actuators was not detectable through these routine procedures, allowing aircraft to return to service with compromised systems that appeared to meet all maintenance standards. The thermal effects creating hydraulic system degradation were particularly pronounced during missions requiring sustained high-altitude operation, where the combination of low ambient temperatures and high internal heat generation from hydraulic pumps created thermal gradients that exceeded design assumptions. Component materials had been selected and manufactured to meet specifications for uniform temperature operation, but the thermal cycling encountered during actual combat missions created expansion and contraction patterns that gradually altered critical clearances within valve assemblies and actuator pistons. Quality control records from this period indicate that aircraft returning from extended missions met all specified maintenance requirements and passed all routine inspections, suggesting that the performance variations being experienced by pilots were not detectable through established procedures. These maintenance records provided engineering teams with data indicating that the hydraulic systems were performing within acceptable parameters, reinforcing confidence in the design while missing the progressive degradation that would prove critical under sustained operational stress. The divergence between instrumentation readings and actual system performance became most apparent during high-G maneuvering sequences, where pilot control inputs required maximum hydraulic system authority. Under these conditions, the reduced control force available from thermally degraded actuators became insufficient to provide the rapid control surface movements necessary for precise aircraft control. Pilots began to experience control responses that lagged significantly behind their inputs, but these episodes typically occurred during high-stress, combat situations where precise diagnosis of system behavior was impossible. Communication between pilots and maintenance personnel during this period reflected the ambiguous nature of the performance variations being experienced. pilots reported subtle changes in aircraft handling that were difficult to quantify and often attributed to external factors such as ammunition loading, fuel distribution, or atmospheric conditions. Maintenance personnel found no obvious defects during routine inspections and interpreted these reports as confirmation that the aircraft systems were operating within normal parameters. This communication pattern reinforced the assumption that the observed variations represented normal operational factors rather than systematic failure indicators. The progressive nature of the hydraulic degradation created conditions where each subsequent flight operated with slightly reduced system capability while appearing to meet all normal performance criteria. This gradual degradation pattern avoided triggering the binary failure detection systems that had been designed to warn pilots of obvious malfunctions, while creating conditions where control authority was progressively compromised. The thermal cycling effects accumulated over multiple flight cycles, creating component wear patterns that were undetectable through routine maintenance, but that significantly reduced system reliability under stress conditions. The physical mechanisms underlying N1K-J hydraulic system failure represented a convergence of thermal physics, precision manufacturing tolerances, and fluid dynamics that created failure modes invisible to conventional monitoring systems. The progression from subtle performance degradation to catastrophic control loss followed predictable physical laws while remaining undetectable through the instrumentation and diagnostic procedures that pilots and maintenance personnel relied upon to assess system status. Understanding this failure chain requires examining the precise thermal and mechanical processes that transformed normally functioning components into sources of progressive system degradation. The hydraulic actuator valve assemblies that controlled the automatic combat flap system were manufactured to tolerances of 0.0002 inches, representing the precision required for reliable operation under normal temperature conditions. These components were machined from steel alloys selected for their strength and dimensional stability, with thermal expansion coefficients calculated to maintain proper clearances across the expected operational temperature range of -40 to +160 degrees Fahrenheit. However, the thermal conditions encountered during extended combat operations regularly exceeded these design parameters, creating metal expansion that altered critical clearances within valve assemblies and actuator cylinders. The coefficient of thermal expansion for the steel alloys used in valve construction was approximately 6.510-6 inches per inch per degree Fahrenheit, a seemingly negligible value that became critical when applied to precision components operating under elevated temperatures. During sustained high-power flight operations, hydraulic system temperatures routinely reached 200 to 220 degrees Fahrenheit due to the combination of ambient heating, pump friction, and thermal load from high-pressure operation. This temperature elevation caused valve components to expand beyond their design clearances, creating gaps that allowed hydraulic fluid to bypass internal sealing surfaces without affecting overall system pressure. The internal leakage created by thermal expansion manifested as a progressive reduction in actuator force output that remained undetectable through conventional pressure monitoring. Hydraulic system pressure gauges measured the pressure maintained by the engine-driven hydraulic pumps, which continued to operate at 1,000 psi regardless of internal leakage rates within individual actuators. The pumps compensated for increased internal leakage by working harder to maintain system pressure, but this compensation masked the actual reduction in force available at individual actuators throughout the system. Flow meter readings during thermally stressed operations continued to indicate normal circulation rates because the increased internal leakage within actuators was recirculated within the closed hydraulic system rather than lost overboard. The flow sensors measured total fluid movement through main distribution lines but could not detect the microscale bypassing occurring within individual valve assemblies. This internal recirculation meant that fluid was moving through the system at normal rates while failing to provide effective force output where it was needed for control surface operation. The automatic combat flap system became the most visible manifestation of this thermal degradation because it required rapid, high-force actuator movement during combat maneuvering. As internal leakage increased within the hydraulic actuators controlling flap position, the system's ability to provide rapid flap deployment and retraction was progressively compromised. Pilots began to notice that automatic flap response lagged behind airspeed changes during high-G maneuvers, but the delays remained within the system's specified response envelope and were often attributed to normal operational variations. Temperature measurement within the hydraulic system was limited to monitoring engine-driven pump output temperatures and hydraulic reservoir levels, but no direct measurement of actuator housing temperatures where thermal expansion was creating critical clearance changes. The instrumentation design had assumed that hydraulic fluid temperature would provide adequate indication of system thermal status. But this assumption failed to account for the localized heating that occurred within individual actuators during sustained high-pressure operation. The physics of hydraulic fluid behavior under elevated temperatures contributed additional complexity to the failure progression. As hydraulic fluid temperature increased beyond 180 degrees Fahrenheit, fluid viscosity decreased, reducing the effective sealing capability of precision clearances while increasing the tendency for internal bypassing. Simultaneously, elevated temperatures caused dissolved air within the hydraulic fluid to come out of solution, creating microscopic bubbles that further reduced actuator efficiency while remaining undetectable through pressure and flow monitoring. Cavitation effects within hydraulic pumps and actuators became increasingly pronounced as thermal conditions exceeded design parameters. The combination of elevated fluid temperature and high-pressure operation created conditions where localized pressure drops within pump chambers and actuator cylinders caused vapor bubbles to form and collapse rapidly. These cavitation events created erosive damage to precisely machined surfaces while producing noise and vibration that pilots attributed to normal high-power operation rather than system degradation. The metallurgical effects of repeated thermal cycling on precision hydraulic components created cumulative degradation that was undetectable through routine maintenance inspection. Each heating and cooling cycle caused microscopic dimensional changes that gradually altered the fit between machined surfaces, increasing internal leakage rates and reducing actuator efficiency. These changes occurred at a scale that was invisible to visual inspection while being significant enough to compromise system performance under stress conditions. Hydraulic system filtration, designed to remove particulate contamination, was inadequate for addressing the metal particles generated by thermal cycling and cavitation damage within actuators and pumps. The standard hydraulic filters were sized to remove large particles that might damage pump mechanisms but could not capture the microscopic metal debris created by thermal stress and cavitation erosion. This metal debris continued to circulate through the system, creating additional wear on precision surfaces and accelerating the degradation process. The point of no return for hydraulic system reliability occurred when internal leakage rates exceeded the system's ability to maintain effective actuator force under high-demand conditions. This transition was not marked by obvious failure indicators, but rather by a gradual reduction in control authority that became critical only during maximum demand maneuvering. Pilots retained adequate control for normal flight operations while losing the precise control response necessary for combat effectiveness, creating a dangerous situation where aircraft appeared to function normally while being unable to respond adequately to combat requirements. Force feedback through the aircraft's control systems provided misleading information to pilots about actual control effectiveness, because the manual control forces required to move control surfaces remained nearly normal even when hydraulic assist was significantly degraded. The control system design incorporated mechanical linkages that allowed manual control force to supplement hydraulic power, but pilots could not distinguish between normal control forces and those indicating hydraulic system degradation. This force feedback ambiguity meant that pilots received no tactile indication of reduced system capability until control authority was insufficient for required maneuvers. The thermal degradation process was irreversible once component clearances had been permanently altered by repeated expansion cycles and cavitation damage. Cooling the hydraulic system to normal temperatures did not restore original component dimensions because the microscopic wear and distortion caused by thermal cycling represented permanent material changes. Aircraft that had experienced thermal degradation continued to operate with reduced hydraulic system capability, even during subsequent flights under normal temperature conditions. Maintenance procedures, capable of detecting thermal degradation, would have required disassembly and precision measurement of internal component clearances, procedures that were impractical under operational conditions and were not included in routine maintenance protocols. The degradation occurred at dimensional scales that required laboratory measurement equipment to detect, making it invisible to field maintenance personnel, who relied on operational testing and visual inspection to assess system condition. The recognition that N1K-J hydraulic systems were experiencing performance degradation triggered a series of attempted corrective actions that inadvertently accelerated system failure while appearing to provide temporary stabilization. These interventions reflected the logical application of established procedures and pilot training to situations that exceeded the assumptions, underlying both the aircraft's design and its operational protocols. The manual reversion systems and backup control pathways that had been engineered as safety solutions became sources of additional complexity that pilots could not effectively manage without complete understanding of the thermal degradation affecting their aircraft's primary systems. Manual reversion capability had been incorporated into the N1K-J's control system design as a backup for hydraulic system failure, but this manual system had been designed and tested based on assumptions about binary hydraulic failure rather than the progressive degradation that characterized thermal stress conditions. The manual reversion system required pilots to overcome hydraulic boost forces that varied unpredictably depending on the degree of internal leakage within the thermally degraded actuators. When pilots attempted to engage manual reversion during partial hydraulic failure, they encountered control forces that seemed normal but provided unpredictable control response depending on the specific state of thermal degradation within individual actuators. The procedure for engaging manual reversion involved pulling hydraulic system circuit breakers to isolate failed components, but this procedure assumed that pilots could accurately diagnose which circuits were compromised. The thermal degradation affecting N1K-J hydraulic systems created a condition where multiple circuits exhibited varying degrees of internal leakage without obvious external symptoms, making accurate diagnosis impossible under combat conditions. Pilots attempting to isolate failed circuits often disabled functioning systems while leaving degraded systems operational, creating asymmetric control conditions that were more dangerous than the original partial failure. Force characteristics during manual reversion attempts provided misleading feedback to pilots about the effectiveness of their control inputs. The mechanical advantage built into the manual control system had been calculated based on the assumption that hydraulic assist would be either fully functional or completely absent. But thermal degradation created intermediate conditions where hydraulic assist provided some force augmentation while being insufficient for full control authority. Pilots experienced control forces that felt nearly normal, while producing control surface movements that were inadequate for the aircraft's actual flight condition. Emergency checklists developed for hydraulic system failures focused on procedures for managing complete system shutdown rather than the ambiguous partial failures that characterized thermal degradation. These checklists assumed that pilots would recognize obvious failure symptoms and follow predetermined steps to configure the aircraft for manual control, but the progressive nature of thermal degradation provided no clear trigger point for initiating emergency procedures. Pilots found themselves managing control systems that seemed to function normally while gradually losing effectiveness, a situation not covered by existing emergency protocols. The automatic combat flap system's response to manual override attempts created additional complications that pilots were not prepared to manage. When pilots attempted to override automatic flap control during perceived system malfunctions, the manual flap controls had to work against hydraulic actuators that were still partially functional but operating with reduced authority. This created a situation where manual inputs fought against automatic systems, producing flap movements that were neither fully automatic nor fully manual, creating unpredictable flight characteristics that pilots could not anticipate based on their training. Maintenance actions triggered by pilot reports of unusual control behavior typically focused on checking hydraulic fluid levels, pressure readings, and external system components. But these inspections could not detect the internal component degradation that was creating the performance problems. Maintenance personnel found normal fluid levels and pressures, leading them to conclude that reported control anomalies were either pilot error or normal operational variations. This maintenance assessment often resulted in aircraft being returned to service with unresolved thermal degradation that would continue to worsen during subsequent flights. The decision to continue flight operations with partially degraded hydraulic systems reflected risk assessment calculations that were based on incomplete understanding of the actual system condition. Pilots and maintenance personnel evaluated flight safety based on the aircraft's apparent ability to maintain controlled flight and perform basic maneuvers, but they lacked insight into the reduced safety margins that thermal degradation had created for high-demand flight conditions. Aircraft that seemed to function normally during routine flight operations had lost the control authority necessary for effective combat maneuvering or emergency response. Temperature management attempts, when pilots recognized that thermal effects might be affecting system performance, typically involved reducing power settings or altering flight profiles to allow hydraulic systems to cool. However, these cooling attempts could not reverse the permanent dimensional changes that thermal cycling had created within precision components. While reduced temperatures might temporarily improve system performance by reducing further thermal expansion, the microscopic wear and clearance changes created by previous thermal cycles represented permanent degradation that would affect all subsequent operations. Secondary failures began to manifest as pilots attempted to compensate for reduced hydraulic system effectiveness through increased manual control inputs and more aggressive control surface deflections. The increased control forces required for manual operation created higher loads on mechanical control linkages and backup systems that had not been designed to carry primary control loads for extended periods. Cables, pulleys, and mechanical connections began to show accelerated wear patterns as pilots relied more heavily on manual control authority to maintain aircraft performance. The electrical systems supporting hydraulic operation experienced increased loading as hydraulic pumps worked harder to maintain system pressure against increased internal leakage. Engine-driven hydraulic pumps drew more power from the aircraft's electrical system while producing less effective hydraulic force output, creating electrical load imbalances that affected other aircraft systems. Generator output monitoring indicated normal electrical system performance, but the increased electrical draw from hydraulic pumps reduced the power available for other critical systems, such as radio communication and engine ignition. Pilot workload increased dramatically as the automatic systems that had been designed to reduce pilot burden became sources of unpredictable behavior, requiring constant monitoring and manual override. The cognitive load of managing systems that provided ambiguous feedback while requiring split-second decisions under combat conditions exceeded the capacity of pilots who had been trained to rely on automated systems for routine flight management. This increased workload reduced pilot effectiveness in tactical situations where maximum performance was critical for survival. Aircraft configuration management became increasingly complex as pilots attempted to optimize performance using manual systems that had been designed as emergency backups rather than primary control methods. The interactions between manual flap control, reduced hydraulic authority, and varying control response characteristics required constant adjustment and created flight conditions that were unstable and unpredictable. Pilots found themselves flying aircraft that demanded continuous attention to basic flight control rather than allowing focus on tactical requirements. The apparent stabilization achieved through manual control techniques was actually a temporary adaptation that masked continued degradation of the underlying hydraulic systems. Pilots who successfully managed partially failed systems through skilled manual control techniques created the impression that the aircraft were functioning adequately while actually operating with progressively reduced safety margins. This apparent success discouraged more aggressive maintenance investigation and reinforced confidence in the aircraft's basic airworthiness, despite ongoing system degradation. Communication between aircraft experiencing similar problems was limited by radio protocol restrictions and the tactical requirements of combat operations, preventing pilots from sharing information about effective techniques for managing hydraulic system degradation. Individual pilots developed personal adaptations for managing their aircraft's specific control characteristics, but this information was not systematically collected or disseminated, leaving each pilot to independently discover solutions to similar problems. The post-incident investigation of N1K-J hydraulic system failures revealed a systematic pattern of component degradation that validated the theoretical framework for thermal stress failure while exposing fundamental limitations in the engineering assumptions that had guided the aircraft's development. Physical examination of hydraulic components removed from aircraft that had experienced control problems provided conclusive evidence of the thermal cycling effects that had remained invisible to operational monitoring systems. These forensic findings transformed understanding of how precision mechanical systems could fail catastrophically while maintaining the appearance of normal operation through conventional instrumentation. Metallurgical analysis of hydraulic valve assemblies removed from high-time aircraft revealed thermal stress patterns that were consistent with repeated heating and cooling cycles beyond design parameters. Microscopic examination of valve bore surfaces showed evidence of thermal expansion damage, with dimensional changes measuring 0.0008 to 0.0012 inches in components originally manufactured to tolerances of 0.0002 inches. These dimensional changes represented permanent deformation that had occurred gradually over multiple thermal cycles, creating internal clearances that allowed significant hydraulic fluid bypassing while maintaining system pressure readings within normal ranges. Surface analysis of actuator pistons and cylinder walls revealed cavitation damage patterns that confirmed the theoretical predictions about hydraulic system behavior under elevated temperature and pressure conditions. The cavitation erosion appeared as microscopic pitting on precisely machined surfaces, with damage patterns indicating that cavitation events had occurred repeatedly during high-pressure operation at elevated temperatures. This physical evidence validated the hypothesis that thermal conditions during extended combat operations had created cavitation within hydraulic components that gradually degraded system performance while remaining undetectable through routine maintenance inspection. Chemical analysis of hydraulic fluid samples from affected aircraft revealed thermal decomposition products and metal particle contamination that provided additional evidence of system operation beyond design parameters. The presence of oxidized fluid components indicated that hydraulic fluid had been exposed to temperatures exceeding 250 degrees Fahrenheit, well above the 200-degree design limit for continuous operation. Metal particle analysis revealed microscopic debris from steel and aluminum components throughout the hydraulic system, confirming that thermal stress had created wear patterns that contaminated the entire hydraulic circuit. Dimensional measurement of precision components using laboratory-grade equipment revealed systematic patterns of thermal distortion that explain the progressive loss of hydraulic system effectiveness observed during flight operations. Components that had appeared to meet visual inspection standards during routine maintenance showed dimensional variations that significantly exceeded manufacturing tolerances when measured with precision instruments. These measurements confirmed that thermal cycling had created permanent changes in component geometry that could not be detected through field maintenance procedures. The correlation between flight hour accumulation and component degradation provided quantitative evidence of the relationship between thermal exposure and hydraulic system reliability. Aircraft with higher flight time totals showed proportionally greater component degradation, with thermal damage becoming severe after approximately 150 to 200 hours of high-performance flight operations. This correlation established that thermal degradation was a systematic effect related to operational exposure rather than random manufacturing defects or maintenance errors. Failure analysis of control system mechanical components revealed secondary damage patterns that confirmed the hypothesis that manual control attempts had accelerated overall system degradation. Mechanical linkages, cables, and pulleys showed wear patterns indicating that they had carried loads exceeding their design specifications for extended periods. This secondary damage provided evidence that pilot attempts to compensate for hydraulic system degradation through increased manual control had created additional failure modes that compounded the original thermal stress problems. Documentation analysis revealed that the engineering assumptions underlying N1K-J hydraulic system design had been based on laboratory testing and short-duration flight trials that inadequately represented the thermal and mechanical stresses of sustained combat operations. Test protocols had validated component performance under controlled conditions, but had not assessed long-term reliability under the repetitive thermal cycling that characterized actual combat missions. This documentation review confirmed that the design validation process had been inadequate for predicting system behavior under operational stress conditions. Comparative analysis of similar hydraulic system designs used in other aircraft revealed that the precision tolerances and thermal assumptions that had proven problematic in the N1K-J were common throughout advanced aircraft hydraulic systems of the period. The systematic nature of thermal stress failure suggested that similar problems might be latent in other aircraft designs that relied on precision hydraulic components operating under high-stress conditions. This comparative analysis indicated that the N1K-J failures represented a broader systematic issue with hydraulic system design philosophy, rather than unique problems specific to one aircraft type. The investigation findings led to fundamental changes in hydraulic system design requirements that emphasized thermal stability and component robustness over precision optimization. New design standards required hydraulic components to maintain operational effectiveness across broader temperature ranges and to incorporate larger safety margins for thermal expansion effects. Component testing protocols were modified to include thermal cycling tests that simulated sustained high-stress operation rather than focusing exclusively on short-duration performance validation. Manufacturing quality control procedures were revised to include dimensional verification using precision measurement equipment rather than relying exclusively on visual inspection and go-no-go gauges. These enhanced quality control measures were designed to detect the microscopic dimensional variations that thermal cycling could create while remaining within conventional tolerance checking procedures. The revised manufacturing standards acknowledged that precision components required precision measurement throughout their operational life cycle. Training program modifications emphasized the importance of recognizing progressive system degradation and provided pilots with decision-making frameworks for managing ambiguous system behavior. The revised training acknowledged that sophisticated automatic systems could fail in ways that were not covered by conventional emergency procedures and that pilot judgment would be required to manage situations where instrumentation provided contradictory or ambiguous information. These training changes represented a fundamental shift from reliance on automated systems toward integrated human-machine decision-making. Maintenance protocol revisions incorporated diagnostic procedures for detecting thermal stress effects that had previously been invisible to routine inspection. New maintenance requirements included hydraulic system temperature monitoring, precision component measurement, and fluid analysis procedures designed to detect thermal degradation before it reached critical levels. These enhanced maintenance procedures acknowledged that sophisticated mechanical systems required sophisticated diagnostic techniques to ensure continued reliability. The regulatory response to N1K-J hydraulic system failures established new certification requirements for advanced aircraft systems that emphasized long-term reliability under operational stress conditions rather than focusing exclusively on meeting design performance specifications. New certification standards required demonstration of system reliability over extended operational periods and under thermal cycling conditions that simulated actual combat or high-stress flight operations. These regulatory changes represented recognition that laboratory testing was insufficient for validating the operational reliability of complex mechanical systems. The systemic lessons emerging from N1K-J failure analysis extended beyond hydraulic system design to encompass broader principles of complex system engineering and validation. The failures demonstrated that sophisticated engineering solutions could create new failure modes that were invisible to conventional monitoring and diagnostic systems. The investigation revealed that precision manufacturing and automated control systems required correspondingly sophisticated diagnostic capabilities to ensure continued reliability under operational stress conditions. The fundamental design philosophy failure that characterized the N1K-J program was the assumption that engineering sophistication could eliminate operational unpredictability through automated control and precision manufacturing. The forensic evidence demonstrated that complexity created new sources of unpredictability that that required different approaches to system design, validation, and operation. The shift from complexity-based solutions toward robustness-based engineering represented a fundamental change in design philosophy that acknowledged the limitations of precision-dependent systems operating under variable stress conditions.